Yeah, so I'm going to talk about computational invariant theory. And I'm going to start talking first about computational algebraic geometry, just a short introduction, because there's a lot one could say about it. Say computational algebraic geometry. So I'm just going to establish some of the notations I'm going to use. So on one hand, we have, I'm going to talk about mostly just affine algebraic varieties, not projective or any schemes or anything like that. So on the one hand, we have affine algebraic varieties over some field K. It can be an arbitrary field. And of course, we have equivalence of this category with the category of, say, finitely generated commutative, and let's say also reduced K algebras. So we have like equivalence of categories or correspondence. So for example, if we have an affine variety X, then we can associate to that a coordinate ring. And if we call that R, then X is just, I'm going to write X is spec of R. And so in particular, for example, affine space, right, corresponds to the polynomial ring in n variables. For now, I'm not going to assume anything about K. So for now, it doesn't have to be algebraically closed or any characteristic. The product of affine varieties corresponds to a tensor product of algebras. Right? If we have a morphism here, let's say phi from one affine variety to another, then that corresponds to a K algebra homomorphism from OY to OX. And if we fix an affine variety X, then we also have a correspondence between subvarieties and ideals. So for example, if we fix X, then on the one hand, we may have a subvariety which corresponds to a vanishing ideal, which I denote by I of Y. So let's call this capital I. And then this Y is the zero set of I. So I'm going to write Z of I. So on this side, we have like radical ideals. Okay, so this is the basic setup. Now, often I will just assume K is algebraically closed, but actually often I will not use that, but it's often easier to write statements. But for computations, often we work just over like rational numbers or a finite field if you just implement it. And in that situation, I write A element of X. If X is an affine variety, just means, right, that A is an element of, is a K rational point. Okay. Now, a monomial, I use this shorthand notation for a monomial in the polynomial ring. And for computations, you know, in the end, almost all our computations will be computations in the polynomial ring. So maybe let M be the set of monomials. And we use some admissible monomial ordering I'm not exactly going to define that. In fact, we just can use one specific monomial ordering, namely the pure lexicographic ordering, which is defined as follows. This monomial x to the power alpha is smaller than x to the power beta if and only if alpha I is beta I for, say, I is 1 to up to k minus 1, and alpha k is smaller than beta k. So this is for some k. So monomial ordering is a total ordering of all the monomials. No, actually, I'm going to actually do it differently. Let me just write it like this. Okay, so in this ordering, x1 is larger than x2, etc. So if we have a polynomial f, then the leading monomial of f is the largest monomial that appears in f. And let's say if we have 0, then I just define it to be 0. If we have a subset of polynomials, then the leading Lm of S will be the ideal generated by all leading monomials. So I'll define this actually, this is actually an ideal, right? So then, so if R is an ideal in the polynomial ring, and sometimes I will just abbreviate this with just kx for short, then a finite subset G is called a Grödner basis if the ideal, if this Lm of G is equal to Lm of I. And now the nice thing is that we actually have an algorithm, given a set of generators of an ideal, then we have an algorithm, namely Buchberger's algorithm, that will compute a Grödner basis for this ideal. I'm not doing a... and this has been implemented in many computer algebra systems. So that's a basic algorithm that we will use for our computations in invariant theory. So, and the thing is that if G is a Grödner basis, then the ideal is generated by this Grödner basis. So that's an important fact. And one other important result is if G is a Grödner basis with respect to this ordering. So this Grödner basis is always with respect to some monomial ordering. For example, this pure lexicographic ordering. So if we use the pure lexicographic ordering, then we have the following. Then if we intersect it with the polynomial ring in xk up to xn, then this intersection is actually a Grödner basis of of this ideal I intersect with k, x, k up to xn. And so in particular, if we take the ideal generated by this, then it's equal to this intersection ideal. So if you have an ideal in the polynomial ring, then we can compute this intersection ideal by choosing this pure lexicographic ordering, computing this Gröbner basis with respect to the pure lexicographic ordering using Buchberger's algorithm. And then we look in this Gröbner basis and only take those elements in the Gröbner basis that only involve these variables. And that will be a Gröbner basis of this ideal. In particular, it will generate that ideal. And so that's. So for example, we can use that to compute things in algebraic geometry. For example, if we have a morphism. Yes?
What do you write with respect to lexicographic order, or what's the P?
Yeah, the pure lexicographic ordering, which I defined here. Yeah. So suppose we have a morphism between affine algebraic varieties. So first of all, this X is some affine variety. So it's some Zariski closed subset of affine space. And so it's given by some ideal. So let's say this vanishing ideal is generated by some polynomials. So let's say these polynomials are given. Again, x is, say, x1 up to xn. This morphism, this y, lies in some other affine space. And this morphism is given by some polynomials, phi1 up to phi mx, right, which is a map from x to y, which is contained in am. So the phi I is the ith coordinate. These phi i's are unique up to modulo this ideal, vanishing ideal. Okay. So now we can look at the graph of this morphism phi. What is this graph? So this is the set of all x, comma phi x, right, where x lies in x. And the vanishing ideal of this graph is, first this x has to lie in x, so we get this equation f1x up to frx. And then y has to be equal to phi of x. So this gives us the equation y1 minus phi 1x up to ym minus phi mx. So that's in the polynomial ring in m plus n variables, x1 up to xn, y1 up to ym. And to find the image of this morphism, so in particular the vanishing ideal of the image, which is the same. Now the image of a morphism may actually not be a Zariski closed set, but you can still look at the vanishing ideal. So it's going to be the same as the vanishing ideal of the Zariski closure of phi of x, right? And that is, lies in this polynomial ring in m variables. So this vanishing ideal is the intersection of the vanishing ideal of this graph with the polynomial ring in the y variables. And so So we can compute this ideal because we can use this Buchberger's algorithm to compute this intersection, right? So we use pure lexicographic ordering where the variables are ordered like this. In particular, the x variables are larger than any monomial in the y variables. Okay, so we'll use this later, but we can use Buchberger's algorithm to compute the image of a morphism, or the Zariski closure of the image of a morphism between affine varieties. Okay. All right, so next I want to talk about linear algebraic groups, or affine algebraic groups, which actually turns out to be the same thing, although you might define them in different ways. Okay. So an affine or linear algebraic group I mean, it's just a group where all the operations are morphisms, right? So it's an affine variety G with morphisms M, G cross G to G, and I that goes from G to G, and an element, you know, the identity element, satisfying group axioms. So, so M is the multiplication and I is the inverse function. Now, if you're working over an algebraically closed field, then M is just, you know, multiplication, and I is just the inverse for G H in G. So here's some examples. Now the definition of a linear algebraic group is a Zariski closed subgroup of GLN, but it turns out it's equivalent to this definition, but it's not obvious. But so one interesting example is the additive group. So this is just A1 with addition, or just, you know, the field K with addition, if K is algebraically closed. In that case, GA is just a affine variety, right? And the coordinate ring is just a polynomial ring in one variable. And then the multiplication is just addition, right? So in terms of ring homomorphisms, or algebra homomorphisms, this multiplication is a map from KT, like homomorphism from KT to the tensor product, right, which is a polynomial ring in two variables. And M star of T is T tensor 1 plus 1 tensor T, right? And the inverse corresponds to the ring homomorphism that sends T to negative T, right? Because that's the inverse in the additive group. And of course, E is just 0. So that's one example. Another example is GLN. So the coordinate ring of GLN, well, first of all, so GLN is contained in a space of n by n matrices, which is a vector space of dimension n square. In fact, it's a Zariski open subset, but you can also view GLN as a Zariski closed subset of a to the power n squared plus 1. Anyway, it's an affine variety. The coordinate ring of the n by n matrices, we can think of it as a polynomial ring in n square variables, but I label the variables Z11, Zij, etc. And the coordinate ring of GLN is then just a localization, where if let's say we take this big matrix Z to be the matrix with these variables, then we can take the determinant of this big matrix, which is now an element in this polynomial ring. And so we localize with respect to that. Right, because GLN is exactly where this determinant is non-zero. So we localize with respect to the determinant of Z. And here, this homomorphism corresponding to multiplication sends Zij to, sum k is 1 to n, Zik tensor Zkj, because that's how matrix multiplication is defined. The identity element is obviously the identity matrix. The formula for the inverse is a little bit more complicated, but you know the formula for the inverse of a matrix. Right, you have to look at this cofactor matrix, etc. I'm not going to write that down. Right. So irrational action of G, where G is some affine algebraic group, on a vector space V is a linear map gamma V to. So first of all, right, we want a group acting on a vector space by linear transformations, but I want it to be regular in some sense with respect to the algebraic group structure. So here's like a formal definition. So V here can, I'm not assuming that V is here finite dimensional, it can be any vector space. But I need more space here. Let me continue here. Satisfying the following axioms. And these are really the axioms of a group acting on a set, but it's slightly different formulated differently. So first, we need the following, and it's like a commuting diagram. So we have this map gamma. We also here gamma. And here we go to OG tensor V. So here we can take the identity on OG and then tensor it with gamma again. And then we go to this space. Or we can also take the identity on V and take this M star, which goes from OG to OG tensor OG. And this diagram has to commute. And the other axiom is as follows. So we have this gamma. Here I have identity. And here I have E star tensor V, tensor identity. So what do I mean by E star? Well, E I can think of as a morphism from a point into G, and then so it's the corresponding algebra homomorphism. So more generally, right, if G lies in G or a K rational point in G, then G star is a homomorphism from coordinate ring to K, which sends F to F of G, right? That's evaluation at the point G. So, so G acts on V as follows, just like this above diagram. So you can take here G star tensor identity. And so then this sends V to G V. So this axiom saying that this diagram commutes means that the identity element should act by identity, which is obviously one of the axioms of an action. And this axiom corresponds to associativity of an action. Now, if the dimension of V is finite, then we can also define rho going from G to GLV. We can define it by, G acting on V is the same as rho G times V, right? So rho G is sort of the matrix with which G acts. And then this action is a rational action. Action is regular if and only if rho is a morphism, it's a homomorphism of algebraic groups or affine algebraic groups, which means it's a homomorphism of groups, and it's also a morphism of affine varieties. So we'll see throughout that we sometimes have group actions of affine varieties on vector spaces, and sometimes these vector spaces are infinite dimensional. But the actions that we're interested in are those like rational actions. It's a little bit misleading to call it rational actions, but maybe a better name would be regular action. But all right. So here's a little lemma that's useful later. If G acts rationally on V, and V lies in V, then the dimension of the span of all the elements in the orbit like all GV, where G lies in G, right? So this is the orbit of V. This is finite. So even though V may be an infinite dimensional space, but the span of all elements in the orbit of V, this is still finite dimensional. And so this follows immediately, or almost immediately, from the way the group acts, right? So we can write gamma of V, which lies in this tensor product. And by definition of a tensor product is just everything in the tensor product is a finite sum of elements in OG and elements in V, right? So in particular, if we look at G, how it acts on V, this by definition is like G star tensor identity applied to gamma V. And that just means that evaluate this Fi at G. So this is just a sum Fig Vi. And this clearly lies in the span of V1, V2, Vr. So this whole thing, this whole span is contained in this finite dimensional vector space. I hope everyone can see this. All right. Right. Okay, now suppose G is okay, let's see, G is an affine algebraic group. X is, say, an affine variety. Then we say G acts on, or let me say that differently, a regular action of G on X is a morphism. I'm going to call it mu from G cross X to X, satisfying the action axioms okay. So in this situation, G also acts on the coordinate ring. So first of all, we have this morphism mu star that goes from OX to OG, tensor OX, right? And then we are in a situation of kind of where we have this gamma, except one tiny detail. If I did it like this, then instead of a left action of G on OX, I would get a right action. This is not so important, but we can just compose here with the inverse on G. And let's call this gamma. Then we see that OX, one can show that OX is GX rationally on the vector space OX via this gamma. And the group G acts by automorphisms, K-algebra automorphisms. Okay, so G acts on this coordinate ring that often is infinite dimensional, but it acts in a nice way. For example, if you take any polynomial or any function in here and you let the group act, then the span of that will be still finite dimensional. All right. So it's just some more notation conventions. Just generally, if you have an action acting on some set, right, then the fixed set I denote by xg, right? So this is all the set of such that it's fixed by every element in the group. A map from x to y is called G equivariant if phi of gx is g times phi x. So the action commutes with the map for all g and g, x and x. A subset here is stabilized by G. I don't want to call it G stable because that's maybe a term that's overused, but it's stabilized by G if Gs is equal to S, where this means the set of all G, S, S and S. All right. All right, so let's look at the situation again. By the way, so in this situation, where we have an affine algebraic group acting regularly on an affine variety, I will just say X is an affine G variety for short. Okay, in this situation. So suppose we're in a situation. So this is an affine G variety. So then G acts rationally on O of X. And so then we can also look at everything that's fixed by G. And this is the invariant ring, right? So this is, well, I already defined what it is, right? Set of all polynomials that are fixed by G. G acts by automorphisms on this coordinate ring, and then it's not hard to see that this invariant ring is actually also a subalgebra. Sub-K algebra. And so this is the invariant ring. or invariant algebra, if you like. Now, it's not always, in all generality, it's not always finally generated. And so if it's not finally generated, it kind of goes a little bit outside the scope of affine varieties. But certainly if it is finally generated, then we can define X, this sort of quotient notation, which we call the categorical quotient, is the spec of this invariant ring. So it's the corresponding affine variety. So I'll just call this a categorical quotient. Or, in fact, it comes also with a morphism from X to this quotient. Namely, we have this inclusion of the invariant ring. This corresponds to a dominant morphism pi x to this quotient. It's dominant in the sense that the image lies dense inside here. In general, it doesn't always have to be surjective if G is not reductive. And this is a quotient in the sense that like this pi is constant in orbits, for sure. And it has some universal property, like any map from X to some affine variety that's constant in orbits factors through this quotient in a unique way. So some kind of universal property. Okay, so the things I'm going to be interested in this course are sort of the following questions. Like, well, basically, how much of these things can we actually compute? So one very basic question goes back to Hilbert, right? Hilbert 14 problem, which what I'm going to write down is not exactly Hilbert's 14 problem, but it was kind of the main motivation for Hilbert. Namely, the question, is the invariant ring finitely generated? Hilbert's 14 problem said something slightly different, like the question, first of all, you can think of this invariant ring as the intersection of this coordinate ring with the invariant field. And so it's the question, if you have, Hilbert's question was basically if you have a polynomial ring and you have a subfield of the quotient field of the polynomial ring, is the intersection with the polynomial ring always finitely generated? In any case, the answer to both these questions is no. Right? So Nagata gave a counterexample, I think in 1959. If I have time, I might give a counterexample, not Nagata's, but a smaller counterexample. I don't know if I'll get to that. So first the question is maybe when is this invariant ring finally generated? And by now you know that if G is a reductive group, then this is finally generated. There may be some cases outside of that where you may also be able to say that it's finally generated. But as you know, there are counterexamples. But certainly, if it is finally generated, then the question is how to compute generators. And the third question is, suppose maybe the special case, if X is, for example, V, where this is a finite dimensional, or let's say an n-dimensional rational representation. So just, V is a vector space, a finite dimensional vector space on which G acts rationally. Then O of V is just a polynomial ring. So find, so instead of actually giving the generators, can you give some degree bounds to which degree one has to go to find all generators? So find an upper bound for what I call beta OVG, which is the smallest d, such that the invariant ring is generated by invariance of degree less or equal than d. And in some sense, I mean, these questions are, of course, related. If you had the degree bound, then if you could just compute invariance degree by degree, which is actually not so hard, because that's essentially linear algebra, then you could just go degree by degree up to this bound that you have, and then you have found a generating set. So if you were able to give some a priori bound for the degree of generating set of invariants, then you would be done. All right. Now, that would only apply, like in this case here, where you have a rational representation. But in the general case, you might also want to find some kind of bound, although you may not have a grading. So I actually have the following result. That's actually useful. So there's sort of the general case where X is an arbitrary affine G variety. And there's sort of the special case where you actually have a vector space and the group acts linearly. And then in some cases, we can actually reduce the general case to the special case, which is sort of easier to deal with. And that uses the following proposition. So if X is an affine G variety, then there exists an n-dimensional representation here for some n, and a G equivariant closed immersion of X into V. Right? So closed immersion means, right, that on the level of coordinate rings, we have a surjective homomorphism of K-algebras. So the proof is as follows. So I'm giving the proof because you might actually, if you want to actually do computations, you might actually need to construct this explicitly. So how do we construct that? So let W be a finite dimensional subspace, and generating, and it should generate the coordinate ring, right? So you just take some set of generators and take the span of that. Okay, this is finally generated. And without loss of generality, by the lemma, I may assume that this W is stabilized by G. So if you let G act, so this group G acts on this, but it also acts on this W, right? Because of this lemma, do I still have the lemma somewhere? Oh, there, right? So I can take generators of the algebra and then take the span of the orbits of those, then I get some subspace that's stabilized by this group. Now we choose a basis of W. So N here is the dimension of the space W. And this V that I'm going to construct is actually the dual space of W. So we have this inclusion which extends to a G equivariant K algebra homomorphism from OV to O of X. I forgot to say surjective also. Right. This here is just a polynomial ring in x1 up to xn. So if I say where x1 up to xn go to, then I just get an algebra homomorphism from this polynomial ring to this algebra. And everything is sort of already G equivariant. And since W generates this algebra homomorphism will be surjective, right? And so let's call this phi star. Then this phi star corresponds to, this phi that is this, should have called it phi, okay? So that gives us the J equivariant. So this is nice because, now for example, if we look at this phi star, this algebra homomorphism goes from this polynomial ring to OX. And G acts, G also acts on this vector space V, right? So this is exactly the situation we're in.
So why is it so different?
Sorry?
Why is it so different?
Because so this W, right, is contained in here, which is exactly all the polynomials of degree 1, homogeneous polynomials of degree 1. W generates this ring here.
Oh, sorry.
Yeah. So by construction. So since it's equivariant, right, it will map invariants to invariants. So you could take generating invariants and then look at the image and they will be invariants here. Now, the nice thing is, under certain conditions, which we'll explain later, now I'm just going to say sometimes we have equality, or if we don't have equality, then there may still be some nice relations between this and that. So maybe this is a finely generated module over that, or something like that, depending on the situation. But what this proposition allows us to do is basically reduce the general case to the case of a representation. At least in some situations. Okay. Right. I have not much time left, but the first situation I'm going to study is so-called linearly reductive groups. These are groups for which the representation theory is particularly nice. So let's say G is an affine algebraic group. And the different ways of defining linearly reductive, I'm just going to choose one that's kind of, one definition that's convenient for what I want to do. First of all, if G is an algebraic group, then G acts on itself, right, by left multiplication, and also on, right, so G is a affine G variety, and so G also acts on its coordinate ring, and it also acts on its dual space, although this dual space can be actually a fairly big space, right, because if G is not finite, and this is a countably dimensional vector space, and this dual space is uncountably dimensional. But anyway, if you have an action of G on the vector space, it also acts on this dual space. So here's a definition that I'm going to use. G is linearly reductive if there exists a so-called Reynolds operator R, which lies basically in this dual space, and is G invariant. And like normalized such that R1 is equal to 1. So in other words, what that means is R is a map from OG to K. And it's G invariant, which means that if I take some function on the group and let G act on it, then this R is invariant under that. So for all G in G and F in OG. I see I'm out of time. Let me just give you one example, and the next time I will give more examples. Because what is this Reynolds operator? You have to think of this Reynolds operator as an averaging operator. So one example, let's say G is a finite group, and the characteristic of the field does not divide the group order. Then we can take this map R to be RF is just you average it over the group. So this f is a function on the group. Now you take just the average value. I'm dividing by the group order, so this has to be invertible in the field. So if G is a finite group and the characteristic does not divide the group order, then G is linearly reductive. Okay? Sorry? Yeah. Yeah, now I see what you mean. Yeah. No, this is correct. This R is now only defined on O of G, but more generally, if you have an affine G variety, X, right, then from this you can construct, and I will do that next time, you also can construct a map from, say, coordinate ring to the invariant ring. And I will denote by R of OX. And you can also call this a Reynolds operator. But in some sense, it's this R kind of acts on this. This is the way I think of it. This R acts on this space, and the action maps this to the invariant ring. Okay. So for other linearly reductive group, you can think of this R also as an averaging operator. And in some sense, well, anyway, we'll talk about that tomorrow. Thank you.
Okay, I realize we're slightly over time, but let's ask if there are any questions for.
In 2, you wrote how to compute generators and question 3. I was wondering if you know it's finally generated and you have a bunch of generators and they actually generate, is this easy to check? I mean, you don't know a priori that they are, but let's say I tell you they are. Is there a way to prove this, or is that hard? Because I know finding the generators to begin with, but you know not much about it. I know that is computationally difficult, but what about checking if a set of potential generators generate or not?
Yeah, so there's several answers to the question. Like, in some situations, you might, for example, know the Hilbert series of the invariant ring a priori. And if you know the generators, you could calculate relations between the generators, and that way you could also compute the Hilbert series of the algebra generated by these generators that you have and compare if these two Hilbert series are the same. In some situations, we also have, for example, in some situations, you may know something geometrically, like, for example, that the set of generators that you have found are separating invariants, meaning that they kind of separate all the orbits that the whole invariant ring can separate, and then there may be some kind of closure operations that you need to do, which might give you a criterion of whether you have already the whole invariant ring. So there may be various situations where you could conclude that you have the whole invariant ring, even if you did not have, say, the degree bound, for example.
Other questions from the room or in Ibadan? Okay, turns out this was a very clear talk. Thank you so much, Arm.
Thank you.